Here we go, talking about the ideal gas law, the last part of our gases section. And you can see here that the ideal gas law equation, which you need to get down in your notes, is PV equals nRT. Go through the variables here real quick. We have pressure, always has to be in atmospheres, volume in liters, N is representative for moles of a gas, R is a constant, it's a value of 0.0821 liter atmosphere divided by mole Kelvin. This is always given because it is a constant. And temperature, of course, always has to be in Kelvin. So let's dive right in, use this equation, and solve one of these problems. So I'm looking for what is the pressure, so there's my variable P, of nitrogen if there is 0.50 moles, so moles is N, and a 10 liter, that's volume container, and obviously this is my temperature. So over here I'm going to just list my variables. Pressure is again unknown, and it's going to be measured in atmospheres. My next variable I was given here in the problem is N, which is 0.50 moles. I have a volume of 10 liters, and my temperature is 25 plus 273 because I have to get it to Kelvin, and that is of course 298 K for Kelvin. My equation I want to use is PV equals nRT. Again, R is also given because that's a constant. So this is something that you want to make sure you have written down on your equation card, is this constant R, 0.0821 liter atmosphere per mole Kelvin. I know that's a big unit, but it actually is the unit for this constant. So my pressure is unknown, and my volume, so P times the volume, which is 10 liters, equals N, which is moles, so it's 0.50 mole. That's N. R is 0.0821, the liter atmosphere per mole Kelvin. And temperature, which is 298 Kelvin. So I'm just going to solve this side, divide over by 10. So I'm going to divide each side by 10 to get P by itself. And my pressure ends up being 1.2 atmospheres after I solve this problem. So again, make sure you get down this ideal gas law and these variables on your equation card, and know that the constant R, the one that we're going to stick with here, is the 0.0821 liter atmosphere per mole Kelvin. Now there's some variations to the ideal gas law. There's two equations here that you should get down, and these go on your equation card as well. Pressure volume equals grams times that same constant R and temperature divided by molar mass. And you can see over there grams and molar mass. And this one, if we're using density of a gas. So you know to use this equation if the problem gives you density or you're asked to find density. Up here, you know to use this one if the problem gives you grams of a gas or even the molar mass of a gas. Again, all of our units, we need to make sure we convert volume to liters, pressure to atmospheres, temperature in Kelvin. This is the reason. This constant, those units don't change because it's a constant, so everything else has to be converted to match those units. So let's go ahead and take a look at our first example problem here. We have an unknown gas that has a mass of 0.116. So mass is grams. So I'm going to represent that with the letter G. It occupies 25 milliliters. This is volume. And it has a temp of 127 degrees Celsius, so this is my T. The pressure, it says, is 155.3. What's the molar mass? So molar mass is represented by mm. So I'm going to list my variables here. G, or grams, is going to be 0.116 grams. It has a volume of 25 milliliters. I know all my volumes have to be in liters, so I'm going to convert that to liters. And the way you can do this is just set up a simple conversion, and I know that milliliters go down on the bottom, liters on top. In 1 liter, there are 1,000 milliliters. So I'm dividing by 1,000, so it's really just moving the decimal 1, 2, 3 spots. So I end up with 0.025 liters. My temperature is 127 degrees Celsius, so 127 plus 273 is going to give me 400 Kelvin, and my pressure is 155.3 kPa. Again, all of my pressures need to be in atmospheres, so I need to do another conversion here and convert kPa to atmospheres. This is where your equation card comes in handy. So grab your equation card, and you can see over here we have all of our conversions listed. 1 atmosphere is going to be your 101.3 kPa. So 1 atmosphere is 101.3 kPa. I'm going to simply divide here. So in my calculator, 155.3 divided by 101.3, we get 1.53. 533 if you're being correct with sig figs, and this is atmospheres. And it wants to know the molar mass is unknown. Our molar mass obviously is going to be in grams per mole. So I can see here I have grams and molar mass. The equation that involves grams and molar mass is this one. So that's the equation that I'm going to choose to use, and I'm going to substitute in. So pressure is 1.533 atm. Volume is converted here to my 0.025 liters, equals grams of a gas, which is 0.116 grams. So that's G times R, which is 0.0821, and T, which is temperature, which we found was 400 Kelvin, divided by, the whole thing is divided by the molar mass, m. So now I need to solve my problem. I need to get the molar mass on top, so I'm going to multiply each side by the molar mass. So that gets rid of it here, and it gets my molar mass up on top over here. And now I can simply divide by the 0.533 and the 0.025. So on each side here, I'm going to divide by those two numbers to get rid of them here. And I'm dividing this whole thing, which is really just this top numerator, by the same. 0.533 times 0.0251 on the bottom. And then my molar mass is just going to be all of this typed in your calculator and solved out. Typing all this in, we end up with 286 grams per mole as the molar mass of my gas. So there's one example of this variation of the ideal gas law. And let's take a look at another variation here. So here's some more gas law examples. What is the molar mass? So this problem, of a volatile. Volatile, well, if you do not know what this means, this basically means that it readily or easily evaporates at room temperature. So that's something that's important that you should probably know, because we will be dealing with that in class, but it readily evaporates, easily evaporates at room temperature. It fills a flask at 1 atmosphere, so that's my pressure. 20 degrees Celsius is my temperature, and the density of the gas here, so I'm going to label this one as D, is 1.842 grams per liter. So looking back on my previous one, I have PMM equals DRT. So this one has density. If the problem gives you density, that's the equation that you want to use. So that's the equation I'm going to be dealing with here. PMM equals DRT. So I'll write that down real quick here. PMM equals DRT. And it wants to know what the molar mass is. So let's identify our variables here. Pressure, I'm given as 1 atmosphere. The molar mass is unknown. That's my question mark. Density, I'm given as 1.84200 grams per liter. I'm also given the temperature, which is 20 degrees Celsius, so plus 273 ends up with 293 K. And obviously R is my constant. It's always given to you as 0.0821 liter atmosphere per mole Kelvin. So let's go ahead and substitute into my equation now. The pressure is 1 atmosphere times the molar mass, mm, which is unknown, equals the density, 1.84200 grams per liter, times R, 0.0821, times the temperature of 293 Kelvin. Now I just need to simply solve by dividing by 1 on each side here, divided by 1. So my molar mass ends up equaling the 1.842 times 0.0821 times 293, 44.3, and that's consistent here with my sig figs. I have 3 there as my fewest, so 44.3 grams per mole as my molar mass of this gas. Now, you might ask to be asked to find, well, what gas? If you know this gas has a molar mass of 44.3 grams, how could you find out what actual gas it is? And the way you could do that is to pull up an example here for this example is to actually look at, and I'll bring this forwards here so we can see it a little better, this table or a table that you find online or it's in your textbook. You can Google it, but basically you have gases and then you have their molecular weights or their formula weights, their molar masses. And we found our gas to be 44, so I'm looking down the list here, and we actually have carbon dioxide as 44.01. So 44.3 is pretty close, so we would have to make the assumption that I think it would be CO2, and that's a way that you can figure out what gas it is as well.